Good afternoon, everyone. My name is CG and join the Vice Chair for the Aberdeen branch of the Institute of Corrosion. I'd like to say a big welcome to our attendees, and we'll give a few more minutes prior to starting this evening's proceedings. So feel comfortable, get yourself a glass of water, a cup of tea or coffee, and we'll be with you shortly. Thank you. Hello again, everyone. My name is CG Anjoin. I'm the Vice Chair for the Aberdeen branch of the Institute of Corrosion. This evening, we have our branch annual general meeting, which will be followed by a webinar, technical presentation by our speaker for this evening, Dirk van Oostendorp of Corpro, who will be giving us a talk on direct assessment of unpiggable pipelines. So we'll just go straight into our presentation for the evening. We want to say a welcome from the 2022-2023 Aberdeen Branch Committee. The names of our various committee members are on the screen in front of us. And we also want to say thank you to our sponsors, both at the branch level and our company sponsors. And with their continued support, we continue to make the Aberdeen branch a force to be reckoned with within the general national body. Currently, we have 252 ICorr members affiliated with the Aberdeen branch, and we're open to welcoming new members. If you're interested, please check for membership details on the ICorr.org website. So starting our annual general meeting, our branch financial position continues to remain strong. It has been affected by events of the last couple of years, and we're welcoming in new sponsors. So if you know any company or body that will be interested in becoming a branch sponsor or even a corporate sponsor of the Institute of Corrosion, please check for details on the ICorr.org website. For the last couple of years, as you can see from our pictorial in front of us, we've had very strong membership and attendance of our branch events, and that continues to be the case even through now. We've had joint events with the TWI, the Welding Institute, Institute of Mining Materials and Metallurgy, IOM3, the Marine Corrosion Forum, and the Energy Institute, and these continue to attract attendees from all over. In fact, with our introduction of our hybrid events and webinars, we've had an increase in the number of attendees to our meetings, and we continue to appreciate your support in this regard. Our recordings of the webinars that we've had and the technical presentations we've had in the past are available on the ICorr.org website at the link in front of us. And our recordings for the sessions are also available on our YouTube channel. The 2022-2023 branch technical program is what's in front of us just now, and that has been quite a busy year with lots of interesting topics by a variety of speakers. And we'll be having our next talk once we're done with the meeting today, Direct Assessment for Unpiggable Pipelines by Dirk L. van Oostendorp of Corpro. Our next event is actually scheduled for the 22nd of August, and that will be the Aberdeen Branch Corrosion Awareness Day. Details and registration information are currently available on the ICorr website, but please note that registration for this event ends on the 15th of August and it will be on a first come, first served basis. The cost for attending this event is £90, and all other detailed information about the event is available on the website. I just put this up so that we can have a quick read through, but it contains exactly what I've just said. And our maximum number of attendees would be 50. Our key event sponsor is Risco Corrosion, and they have been supporting us for this event. Now, for the 2023-2024 technical year for the Aberdeen branch, we're proposing that Adesi Jan and myself serve as chair and Mei-Ling Chia serve as vice chair for the upcoming session. This was proposed by Dr. Mohammed Ijaz and Dr. Yunan Gao, but if we could have one or two seconders, that would be great. Okay, we have a seconder by Steve Patterson. Thank you very much, Steve. So we are happy to serve, and also by Eric Martin. Thank you very much, Eric. We glad to serve the branch and our members for the upcoming session. So without much ado, our talk for this evening is by Dirk L. van Oostendorp. He's Director of Engineering and Technical Services for Corpro Incorporated, based in Houston, USA. Dirk has over 40 years of global experience in all aspects of pipeline and structural integrity, encompassing cathodic protection, corrosion control, material selection, protective coatings, inspection technologies, and risk management. More recent experience includes integrity monitoring, failure analysis, and pipeline integrity issues. Dirk is a fellow of the Royal Society of Chemistry, a fellow of the Institute of Corrosion, and an AMPP corrosion specialist and cathodic protection specialist. Dirk has undergraduate and graduate degrees in chemical technology and physical chemistry, and was a member of the original INGAA Battelle team that developed what has now become the direct assessment methodology. So without much ado, can we welcome Dirk with a virtual round of applause? Dirk, over to you. Thank you.
Thank you very much, CG. Greetings to everybody from Houston, Texas. And it's kind of nice to see on the list of participants names of some folks that I've known and worked with over the years. I thank you all for attending, and hopefully this presentation will be beneficial to you all. With that, I'm going to bring up the presentation, if I may. And we'll talk a bit about, let's see if this will work. Is that better? Can everybody see this now?
Yes, we can. And apologies, I should have done a little bit of housekeeping. Please keep your computers on mute while the presentation is going on. And if you have any questions and answers, please ask them in the Q&A box. I will address them once the presentation is over. Apologies, Dirk, over to you.
No, thank you. Very good. So yeah, we're going to talk about direct assessment for unpiggable pipelines. We've gone through quite a bit of this background. After several large and fatal pipeline incidents back in 1999 and 2000, The federal regulations changed substantially in the United States with for the pipeline operators. Um, Prior to that, it was much more of a best practices type of environment. But now the federal government required changes to be made to become a more prescriptive process. And so as a result of that, the natural gas pipeline companies and the products and crude pipeline companies have a slightly different approach to how they manage the integrity, and this drove a few processes to occur. So the Interstate Gas Association of America, working together with what at that time was the Gas Technology Institute, gathered a group of people in the industry to develop a methodology that would get to the same level of integrity management for pipelines as other technologies at that time. Let's say at around 2000, 2001, inline inspection was looked upon as one of the leading integrity tools. The problem that we had in the United States was that there were thousands of miles of pipeline where inline inspection was not feasible in any sense, and would have taken large investments or major changes and modifications to the pipeline systems to accommodate the inline inspection. So by looking at other technologies and approaches, we determined that there was ways to integrate some known techniques and gather greater information out of that. And that is how the direct assessment process spawned. It didn't take very long before we realized also at that point that a number of different variations were needed. And this is where external corrosion direct assessment, ECDA, internal corrosion direct assessment, ICDA, and stress corrosion cracking direct assessment were then sort of broken out. And initially back in 2002, NACE International, at that time now AMP, came out with the first draft of the recommended practice 0502, which was then pretty much accepted by the US Department of Transportation. Part of that four-step process, also on the end, the post-assessment is where the operators had to look at the reinspection intervals based on corrosion growth rate for the implementation of the process. So we're going to talk a little bit about some of the background in a bit more detail, and then I'll present some data from some case studies that we've done recently, which kind of show what the results would look like. So again, corrosion, no surprise to us, it's a natural process. Refined metal, ferrous metal objects, whether it's a pipe, tank, or whatever it may be, when exposed to the standard environmental conditions of either being submerged or in soil or in the atmosphere, is going to corrode to a chemically more chemically stable state, like an oxide or a hydroxide. As a result, it's going to change its mechanical properties. When we speak about pipeline integrity, DNV has a very nice definition there. That is the ability of a pipeline system to operate safely and withstand the loads. In Corpro, we've kind of taken a slightly different tact on that, but that we also want to make sure that the current condition of the pipeline allows it to continue in its designed operating conditions, and that the predictable risk of failure can be reduced and managed to some degree. So again, public safety and property protection is a key component of that. So where it all began, as I mentioned, this was back in around 2000 in response to a couple of large pipeline accidents at that time, that a team was assembled. The whiteboard on the side there is actually the whiteboard in Columbus, Ohio at Patel's institute there. Dr. Brian Lease was nominated as the leader of the team. Brian was an amazing person to work with. He had years of experience with pipeline safety and pipeline predictive diagnostics there. I think the big thing that made this project successful was that we engaged early on with the federal regulators from the US Department of Transportation to keep them apprised of where the process was going. Although they could never actually approve or disprove a process, being accepting of it would allow it much greater application for the pipeline operators. And then the ultimate piece of this was the task that we were assigned was to develop some sort of integrity assessment strategy as an alternative to inline inspection and hydrostatic testing, simply because a lot of the pipeline systems were not suitable. It was unfeasible to use either of those techniques. So that's sort of the history behind that. On the other side, there was the regulations that came out. So in 2001, pipeline operating companies in the United States for interstate pipeline systems were required to develop an integrity management program, a pipeline integrity management program. It had to be a written and prescriptive process. Best practices were no longer acceptable, so there had to be a very prescriptive document that was then auditable by the federal authorities. Again, in 2002, NACE at that time published the first pipeline external corrosion direct assessment methodology. And we're starting to see more adoption of some of the NACE or now AMP recommended practices being accepted in other parts of the world, Central America, for example, in Mexico quite heavily, and other locations as well. So what is external corrosion direct assessment? It's a structured process, and that is what appealed to the regulatory folks. When it's structured, they can actually follow the individual steps that are required and assure that there's compliance there. So the important point here was to improve the safety and reduce the impact of any external corrosion taking place on buried pipelines. The next part of it was somewhat predictive, in that it would also then allow operators to understand where the anomalies were, predict any sort of ongoing corrosion, and then in a prioritized manner address these additional locations on the buried pipelines. 0502 again has come out originally in 2002. There have been multiple revisions to it since it is on the cycle. I think the important part here is we did it in phases so that there are 4 steps. The pre-assessment step is important and often the most underestimated as far as importance and also effort required. The pre-assessment step is designed to review available information and knowledge with regards to a pipeline system, and determine at that point whether or not external direct assessment as a process is applicable, if there's sufficient information to justify it. And also at that point, in the pre-assessment, determine which tools will be acceptable based on the condition of the pipeline, based on physical parameters and topography. From there, it goes into the indirect inspection phase, which is typically your overline surveys along the pipeline to gather the data. The back end of that phase is then the data correlation and risk ranking, which leads to the direct examination phase, prioritized excavations to actually inspect the pipe at pipe depth, conduct some additional in-ditch testing on the pipeline, and then the post-assessment phase is the back end to actually demonstrate that all 4 phases have been completed, demonstrate that the information provided out of the pre-assessment actually did lead to a successful application of the technology. There's a corrosion growth rate calculation portion to the post-assessment, which then also drives the required re-inspection interval for the external corrosion direct assessment application. So as with any good tool, we do know that there are limitations. And this was one of the discussion points with the federal regulators when we were going through the assessment of the process. In cases where there are disbonded coatings, external corrosion direct assessment struggles very, very much so, because the disbonded coatings will then isolate sections of the pipeline, and there is no way for any of the overline techniques to be able to sort of identify defects at those locations. Another area is where the surfaces, if you have pavement or reinforced concrete in areas where there's frost, the use of standard techniques like SIPs and DCVG and even some of the electromagnetic techniques suffer, so the accuracy is compromised. They're not possible. However, there are ways to get around that in some cases. For example, in pavement, as we see in the photo, there are possibilities to drill small pilot holes and use those as a means to maintain the contact, but that's not always feasible as well. One of the other big considerations is where the measurements can't be conducted in a reasonable time frame, where there's limitations as to how quickly the different techniques can be conducted on the same pipeline. And lastly, if there's a great amount of congestion, so for example, in some of the large cities, we suffer as well, where there are pipe type cables, multiple different underground utilities, conduits, duct banks, and all of the other structures. Under those conditions, there may be limitations as far as shielding or data biasing with respect to the external corrosion direct assessment process. So these are all taken into account in the pre-assessment phase when trying to determine if it's feasible and which techniques would apply. And then from a geospatial standpoint on the back end, one of the important things is being able to have the data in a format where it can be aligned and then geopositioned. In this case, it's a typical example of usually the data results. We have a system that converts it into multiple bands. And on top is showing the data on a false Earth background. So with the SIPS data on the top, we're able to identify areas where there are apparent coding anomalies, areas where the potentials do not meet criteria, the DC voltage gradient below that. In this one, there's also current attenuation testing that was done, and then soil resistivity as well, along with the topography of the pipe at the bottom. So this is a snapshot of how all of the data can be accumulated and assimilated very rapidly, since it is geoposition data. From there, the next step is actually going down and doing the excavations after the surveys have been completed, areas have been identified. Here was a location where there was coating damage caused on the pipe. You can also see that there's gouges that resulted. It was a case where one of the cable companies was doing excavations and they crossed over this natural gas pipeline, hit and damaged the coating on the pipeline, and it was never reported. So the ECDA process did pick it up and identify it. When it was found to be aligned with some above ground markers from the communication cables, that's when it was prioritized for excavation, and also one that DCVG picked up very accurately as far as position. Typically other kinds of things that have been found. This was one area where there was also AC corrosion that was identified. So with the current attenuation, we identified a number of these small points. DCVG pinpointed them, and the SIPs identified that there were low potentials as well when they were excavated. There was a metal loss anomaly that was a result from AC corrosion that had taken place due to the power line crossings. Switching gears to stress corrosion cracking. This one has some other considerations that one has to take into play with for example, the location of the pipe, the depth of the pipe, the depth of cover. So for those pieces, we typically would use something like a pipeline current mapper to accumulate this data. The pipe elevation is a large part of that as well. So usually typically sub-meter data to get the geospatial alignment. This is important for the determination of the slope magnitude, whether we have a consistent or if there's any abrupt changes in the topography. Soil characteristics, so drainage, wetlands, and then soil characteristics as far as corrosivity become a big important factor to that. We also know that soil pH is a contributing factor in many cases to SCC. Coating defects usually are aligned and allow for collection of water, groundwater, that then undergoes some changes on the pipe surface. And then also cathodic protection deficiency. So marginal CP is also a known contributor to several forms of SCC. it's rather interesting that if there is past ILI data that can also get factored into this. For example, when we're looking at things like unusual appurtenances, sort of pipe bends, river weights if it's going through wetland areas. ILI is helpful in that, especially if there was a geo module run on the ILI run to be able to sort of get the elevation more accurately as well for verification. Probably one of the uglier looking stress corrosion crack colonies that we were able to detect in this approach. SCC gave us an area that was prone. SCCDA rather gave us an area that was prone to it. Using a couple of the techniques, we found a specific coating anomaly where the potentials were low. The soil was rather alkaline, and when it was excavated and cleaned, the crack colony, we didn't even need NDT at that point to prove it out because it's pretty apparent. The good news is the cracks had not coalesced to failure point, but it was quite encouraging to be able to identify it this accurately. And the pipeline operator ultimately ended up having to cut this section of pipe and do a replacement because composite reinforcement wouldn't have satisfied the mechanical requirements at this location. So let's switch the gears just a little bit then, and we'll talk about internal corrosion direct assessment. This one's a little bit more complicated in some ways, and still a four-step approach, but there are certain other factors that we need to take into consideration. So again, it's still the structured approach. One of the things that we try to do is anticipate where we may have future locations along the pipeline where defects could be progressing. And so from the internal standpoint, if we're thinking about on the natural gas side in particular, one of the things we're looking at is exactly where we do have water accumulation, water pooling, and where there's enough momentum of the flow stream to be able to carry the water through. So there's the inclination angle, and we get to the critical angle assessment to determine where that water is going to get trapped and where it's going to carry through. The initial ICDA protocols were released in 2006, and that was for liquid petroleum pipelines. They were somewhat easier to assess, and so that was the first one that was treated. After that, we understood the differences between wet gas, for example, multi-phase flow, and then finally, there's a condition where if you have large cross-country gas pipelines that are transporting what would be considered normally dry gas, with the exception of, let's say, dehydration interruptions or anything like that, there was a separate recommended practice, standard practice that NACE released for these. So from the ICDA standpoint, there are four different standard practices to follow depending on the conditions of the pipeline that we're going to be looking at. So one of the first things we're looking at is a reference at top to 192.927. So that is a direct piece out of the federal regulations, which sets out some of the requirements for how one needs to assess the internal corrosion on the pipeline. So the first thing we're looking for are areas along this particular pipeline that's under study where water or any other electrolyte may accumulate. This can be water that's trapped in the flow stream itself. It can be water that forms due to condensation. Closer to production systems, it's also possible that there's water carryover from the dehydration process, or if there's again, interruptions in the dehydration that allows wetter gas into the system. What we want to do is really focus in our attention along this pipeline to the areas where the internal corrosion has the highest likelihood, following the four steps again, as we did with the other direct assessment protocols. If an operator has included ICDA into their integrity management plan, There are a few more pieces that are required by the federal regulators. So one of them is, for the very first time that one applies the internal corrosion direct assessment process, the criteria is a little bit more restrictive as far as demonstrating the applicability. It's going to take into consideration the analysis is done on the entire pipeline, but the remediation is only limited to the covered segments. And in this case, the point there is the regulations focused in on what are called high consequence areas along the pipeline, which have set criteria published by the Department of Transportation. So even though you are assessing the entire pipeline, from the regulatory standpoint, you're only required to focus in most heavily on these areas that are high consequence. And most recently, with what's been talked about as the mega rule, there are now moderate consequence areas defined as well. So the pre-assessment phase here is gathering the data, making sure that the ICDA process is feasible and applicable, and then begin to start to look at the modeling that's going to be required in order to determine the movement of the electrolyte and water in the pipeline, identify the specific regions along the pipeline where internal corrosion could be a concern, and then compare that with these high consequence areas. Look at the accumulation point or where entrainment may be taking place. Data information, important pieces here. All the data elements that are considered by ASME B31.8S, the physical and historical operating parameters must be available for inclusion in this. Information for the model. So if we're thinking about running a flow model to do these calculations, typically we would use something like Olga in order to make this sensible. There's quite a list of important pieces of information, such as the flow rates, the pressures, the temperatures of the flow, the chemical composition, all of these pieces together, along with detailed information on the elevation profile of the pipeline that allows us to look at the low points and actually do the critical angle assessment. Operating data, especially if we're talking about what would be a normally dry gas pipeline, as far as the frequency and magnitude of any upsets on the dehydration system or any changes that have occurred. And then if there is any scraper ILI use in the past, as far as previous data that could be helpful. All of these pieces get blended in together to develop the process and allow the fullest analysis using the internal corrosion direct assessment. So the region identification then is another issue, as I mentioned before, because the federal regulations focus mainly on the high consequence areas or now moderate consequence areas. So although you may be working across an entire pipeline section, there may only be specific areas where you need to have this level of detailed information. Oh, I just saw a question pop up. Billy, for subsea pipelines, the answer is yes. That is true. These can be applied to basically any of the pipelines for gas and liquids, both onshore and offshore. So the approach would be there. The data requirements, I think, is the piece that's the stringent thing. So for offshore, you would need a very good detailed profile of that pipeline. So again, if we've got a high consequence area in some of these colored red pipeline route, we're running the internal corrosion direct assessment across the entire line, but then only going into very detailed analysis on the covered area. There's a question about coding defects on HDD. I'll come back to that one because there are considerations there that make that complicated. And so when we start to look at the ICDA, one of the big issues here is that we may have a region, but it may actually cover more sections as far as the high consequence or moderate consequence. And this is where the Gas Research Institute had some additional guidelines that are useful when it comes to actually modeling out these regions. And if the operator chooses not to follow that specific requirement, they have to then determine and demonstrate the applicability of whatever other model it is that they wish to use. So then we turn into the flow simulations. This is, again, quite a process. We start to develop the digital elevation model, electronic wire line of the route of the pipeline, the topography of the pipeline and profile in 3 dimensions. So wherever there's changes or bends or whatever, that's all taken into consideration. We do the inclination angle, the critical angle assessment to sort of determine if there's any specific areas where water holdup may become more of a problem. And then one of the key things is to evaluate the water residence time. I'll talk about that and show examples of that. But when we start thinking about this, there's steady state models and there are transient dynamic models, and a big difference there. The best way to think about that is that the steady state model assumes uniformity of the flow stream going through the pipeline, and that, you know, if there's any water in the gas or in the product, it's going to be uniformly dispersed. And that may not necessarily always be the case. And this is where that transient digital model becomes critical for the analysis, because you can have the water present in many different phases. You know, it could be sort of emulsified water in there. It could be droplets that are moving, and the droplets may be moving at a different speed than the flow around it. You can actually have stationary water films that get stuck at welds or other low points. You can get a stratified film where it separates out from the flow stream and starts to move along the surface of the pipe at a specific part of the circumference of the pipe. So these are very important to consider, and this is why my personal preference is working with a program like Olga. So let's take a look at some real data. Here was a dynamic analysis that was done on a specific pipeline. Looking at the lower half, you'll see the dotted green line. That is the profile of the pipeline in meters. So going down a hill, going across a flat area, and moving back and forth. It was a natural gas pipeline, actually gas and gas condensate. And so when we ran the model and then turned on the composition tracking, we could actually start to see the gas fraction, the water fraction, and the condensate fraction as to where we would have water dropping out. And so it becomes rather visual. You can see where the water is the highest concentrations. So at about 126 meters down the pipeline route, you'll see that there's a large area of water that's potentially being trapped there. But moving over to around 209 meter, you'll also see a peak there. So there is some carryover that gets trapped at the top at that plateau. Moving over to the area around between 350 and 378 meters, you would normally think that in a low point, that's where the highest accumulation of water is going to be. But in this particular case, that wasn't true. It was actually on the uphill portion of that next pipeline rise. And then there was carryover, which allowed water to deposit on the downslope side at around 540. So this is where the composition tracking became very helpful. Let's see a couple more questions. I will promise I'll come back to those. So once we have the composition tracking, the next piece is to then project this out in a little bit more detail. And I mentioned the residence time of the water because that's a critical element to us. Even though I may have a high mole fraction of water, if that water is moving through the pipeline rapidly, it's not going to become a concern for us, or lesser of a concern than areas where I have trapped water. And so in this particular case, what we then did is use the transient simulated portion of the Olga model to take a look at the transit time of the water through there. And so you can see that in some of the cases, we we were looking at water residence times, in tens of hours. Whereas in other areas, we were in the 12 to 15,000 hours of residence. And so, interestingly enough, when we projected out known smart pig indications, ILI indications in this same area, we could see that this lined up very well with the areas where we had very high water stagnation, where the transit times weren't, where the water actually resided in there for hundreds and thousands of hours of time. So, the confidence there was quite good. Taking the data one step further and projecting that out onto the topography of the pipeline, we can actually see where this was in space. So again, the graph on the right-hand side is the overall length of it. The snippet in the red box is actually what's shown there in 3D, to where we can actually see the flow and where the water is getting caught on the uphill rises on the pipeline coming out of some of these depression points on the pipeline. It's somewhat counterintuitive in that sense, that those are the areas where the highest amount of water would be found, as far as the number of hours that the water is staying there. In the one case in particular, I think it was the second location downstream, what we found is that with the modeling, when we did the dynamic modeling, there was almost a reflux situation that was taking place there, where the water would actually rise up the uphill slope, but then start to slide back down because there wasn't enough momentum in the gas stream to push it all the way. So there was almost a reflux at that particular location. And that was an area of interest to us for further inspection using NDT. The direct examination in the case of the internal corrosion is not quite the same as what we do for ECDA. Of course, it's on the internals. So typically we would end up using something like long-range guided wave ultrasonic as the first tool to assess for the internal corrosion and do the confirmation. If there are indications found and confirmed, this is where something like phased array or automated UT would be used to map it out further. According to the regulations, if there is any corrosion identified, it's important to evaluate the overall severity of the corrosion at that location, identify potential remediation methods. If there are any discrepancies, it may be necessary to conduct additional digs. And this is where it sort of gets a bit awkward, because you're also then required to evaluate the potential for internal corrosion, even if it's not in these high consequence areas. But if there's a severe location that wouldn't be from a public standpoint, they will also require further investigation. So on the photo on the right top, there's a guided wave tool being installed on the pipeline to do the shots. Bottom photo, this was in what the operator was convinced was a dry natural gas pipeline. Yet if we look closely, we can easily see the water tracks from where the water was flowing along the bottom of the pipeline. And there at the very bottom, at the 6 o'clock location, there's plenty of corrosion with several very large metal loss pits in there. This is where ICDA determined that there was water sitting in there for about 3,000 to 4,000 hours before it would actually move through. And so there was a constant flow, but there was also water trapped in there. So good confirmation for the technique being functional and working. The post-assessment phase, then we have to look at the overall effectiveness, demonstrate that it really worked. If there was any corrosion identified, complete root cause analysis to understand what was causing the problem. Update the risk assessment. This is a requirement as well. Kind of a standard format is shown on the top left there in a risk box. If there are any complications or sort of blind spots found in the technique, it's necessary to change the inspection strategy. And then if there are severe enough locations with corrosion taking place, but not to the point where they mandate repairs, continuous ongoing monitoring may be required. And that can consist of online chemical analysis of the liquids that are flowing through the pipeline to monitor any trends for the corrosive elements. It can also go to installation of permanent UT sensors or electronic probes at the specific locations. As seen there on the left, there's a PermaSense UT detector at the top of a 90-degree L, which was found to be highly corrosive area. And then similar to the other direct assessment processes, one is required to determine the reinspection interval based on corrosion growth rates. So those are all the steps in the process there. Give a couple of really interesting case studies. So this was a comparison and a blind comparison between ILI results and ICDA results using the pipeline inclination profile, the flow modeling. It was possible to identify areas where water retention may have been an issue. And when that was then compared, it matched up quite well with exactly where the ILI defects were identified. There were a certain number of ICDA sites that did not necessarily have resulting corrosion or very minor corrosion, but the majority of the results lined up incredibly well. So you can see the small bands going across the top. Those were the predicted ICDA corrosion sites, and the red and the green were metal loss anomalies identified by ILI, and the critical depth is 50% at that point. So very good alignment there between the real data, real pipeline data. And I think that brings us up to the end of what I had. So I'd like to thank everybody very much for joining in today. My contact details, I'll share those in case anybody has any questions or wants to contact me separately. And again, thank you. And with that, I think I will jump back to a couple of the questions that were brought up. So there was a question about techniques for coating detection, coating anomaly detections in HDD segments. Very good. It's complicated for the external corrosion direct assessment, but separately, what we've used successfully is current attenuation to determine the amount of bare steel at the HDD, whether it is equivalent to the remaining pipeline or whether it's any deeper. And also some indication of the percent bare coating in that location. So AC coating attenuation does work quite well on HDD spans. Coating disbondment, tricky. So most of the DC-based ECDA techniques, for example, SIPS, DCVG, will have a real problem if there's desponded coatings or coatings that can despond. The AC techniques have been slightly more successful in being able to identify areas where there is despondment taking place. That's the difference between, for example, with the DC, we're based on using the cathodic protection. And so we're flowing the signal from the outside of the pipe to the pipe, whereas with the AC-based techniques, you're connecting the signal generator directly to the pipe and looking for leaky areas where the signal's exiting the pipe. So despondent coating is a problem for all of the direct assessment. I would say that things like pipeline current mapping and AC current attenuation have been a little bit more successful in identifying despondent areas. There's a question about the flow modeling. Very good question about whether underground pipelines, if there's data missing. So this is one of the requirements where when you're doing the assessment, if there isn't sufficient data to support the flow modeling, ICDA is no longer a possibility. Now, determining the elevation, if that's not accurate, it may require a pre-survey where a team will go out with an accurate electromagnetic pipe locator to get the depth of the pipe and a GPS system at that point to get the coordinates so that you do have the X, Y, and Z and are able to build the wireline profile of the pipeline. So that can be done. If there's a lot of missing information, or let's say where as you mentioned, the as-builts are not available or incorrect, there are some limited capabilities to be able to correct for that. But in other cases, the ICDA may not be applicable as a result of that. Stephen, situation where a pipeline has been an intermittent service, would ILI then be compulsory? Depending on the operating conditions of the pipeline, there are different ways to approach that. And again, whether it's a regulated pipeline or not, ILI is one of the accepted 3 techniques now. So ILI, hydrostatic retesting, and direct assessment. If it's proven that the direct assessment approaches may not be applicable or may not be feasible, one would look to either hydrostatic testing or ILI. And then we would be looking at whether or not there's facilities to be able to accommodate either of those. Single flow pipelines, for example, hydrostatic retesting may not be a very good practical solution if it's going to cause major interruption. But there have been cases, for example, where it's been possible to use tethered ILI, for example, as a means to be able to do that if there's insufficient flow. So it's not compulsory. It's one of the options that an operator is allowed, but you still have to justify which approach is the most acceptable based on the regulations. Cost comparison versus ILI. So the direct assessment on average, and this is always difficult, but on average, is considerably cheaper than the ILI runs. And that becomes even more of a case if we're talking about older pipelines where any accommodations need to be made. So for example, if there are field bends or wrinkle bends, or if there are any valves that may not allow full passage. But typically, the ICDA process is the most expensive because we're running Olga. But as far as SEC and ECDA, it's noticeably cheaper, let's say, than a conventional ILI run. The risk assessment matrix, no. This was specific to the one particular operator. This is where they got to set their thresholds and determine what they perceived as the highest risks to that specific pipeline. If an operator develops their own risk matrix, it has to be in line with their integrity management plan and approved by the regulatory agency. I think I've covered them all. If there's anything else,
Thank
by all
you,
means.
Dirk. That has been quite informative and quite thought-provoking, to be honest. Some of us are pipeline savvy, as you've kind of surmised from the questions that you've been fielding, and some of us are still neophytes into the world of pipelines and integrity management processes which apply. So we'd like to say thank you for the presentation and the questions. And could I ask the branch to give a virtual show of appreciation for the wonderful presentation we received this evening? So this brings us to the end of our presentation.
Thank everybody for joining in, and
go ahead, Dirk.
And hopefully the next time I can do it in person. There's my promise.
That'll be fantastic. I will hold you to that. So our next event is lined up for the 22nd of August, and that would be the Corrosion Awareness Day. Please check the website for details and register. We'd appreciate your attendance. Thank you and have a lovely evening. Goodbye.